कुन्देन्दु तुषारहार धवला या शुभ्र वस्त्रावृता या वीणा वरदण्डमण्डितकरा या श्वेत पद्मासना या ब्रह्माच्युत शङ्कर प्रभृतिभिर्देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निशेष जाड्यापहा।
Good morning, everyone. I, Kiran Gupta, Assistant Professor, LCIT College of Commerce and Science, welcome you in the next webinar on the topic Fiber Optics Perspective in Communication. We have been sent blessings for the webinar from our respected Chairman, Mr. Pramod Jain sir, Vice Chairman, Mr. Ankit sir, and Secretary, Mr. M.K. Agrawal sir. LCIT management is very helpful and always encourage us to conduct such intellectual programs. The aim of such programs is to encourage students toward inquisitiveness and dedication for the future avenue in the field of science. We have with us our respected Principal, Dr. Archana Shukla ma'am, who always encourage us and giving guidelines for conducting such events. I heartily welcome our respected Administrative Officer, Mr. Abhinav Paul sir, who provide us direction and assistance to conduct such programs smoothly. I also welcome our Coordinator of Science, Mr. Abhishek Keshavani sir, Convener, Mrs. Pratiksha Pandey, all faculty members and participants. For this national webinar, we are honored to have eminent speaker, Dr. Shikha Jaiswal, Firoz Gandhi College, Raebareli. She is Assistant Professor of Physics. She speaks on the topic Fiber Optics and its perspective in communication. I heartily welcome you, ma'am. The aim of this webinar is to create awareness and encourage research studies in this field. I hope you all will have an intellectual time. So let's start with the God's grace. Now I hand over the mic to Mr. Abhinav Paul sir. Thank you.
Greetings to all the participants who have taken out their time to visit us. Especially I want to welcome Dr. Shikha Jaiswal ma'am amidst us. Thank you very much, ma'am. Namaskar. Thank you for joining us. I hope you're all good, hale and hearty for this event today. And we are sure that we are going to be enlightened. Well, I'm no expert to talk about this topic, but I'm sure about one thing, and that is this, that one particular thing that has changed the world is communication. And any technology, any sort of technology that makes the communication possible, much more easier, convenient, and to reach to door, hand to hand, ear to ear, and eye to eye is very pivotal. And this is what optic fibers has been doing. We all need communication in somewhere at one point of time. And that communication is what this particular seminar is going to talk about, of its feasibility, of its accessibility. So I thank you, Dr. Shikha Jaiswal, ma'am, for accepting our invitation and joining us. I also want to extend thanks to our patrons, our chairman, Sir Shri Pramod Jainji, our vice chairman, Shri Ankit Jainji, as well as secretary of the society, Mr. M. Agrawal, Sir, for giving us their consent to organize this webinar. I want to thank Dr. Archana Shukla ma'am, who is always zealous about making the college do such events so that the edification of knowledge and the inquisitiveness to do the research is inculcated from the very beginning in our students. I extend my greetings to the head of the science department, Mr. Abhishek Keshwani sir, as well as the convener of this program, uh, Mrs. Pratiksha Pandey ma'am, for organizing this event. Without much ado, I would request the principal of the organization, Dr. Archana Shukla ma'am, to kindly lead us forward.
Good morning to all the distinguished guests and participants who have chosen to connect with us today. It gives me immense pleasure to welcome you all today to this event. In times of COVID-19, following social distancing norms, we managed to find a way to gather and garner knowledge in the emerging field of fiber optics and its perspectives. Again, I would like to thank all of the participants and distinguished guests who have chosen to connect with us today. Physics is one of the basic streams of science which has made it possible for the human mind to understand and make sense out of the vast universe and how it justifies the existence of every element that is present on the face of Earth. Starting from the string theory to the concept of black hole, physics has everything to do with anything that we come across every moment of our life. Physics as an intent, this webinar intends to capture the youth and encourage them to venture into this field to learn, absorb, and enrich their minds. Let us try to connect with the researchers who have dedicated a substantial amount of time in making these new technologies more and more accessible to the people. One this field is fiber optics, defined as the science of transmitting data, voice, and images by the passage of light through thin, transparent fibers. In today's world, we are surrounded by big data clouds, starting from the internet to the smartphones and tablets. Fiber optics provides the ability to transmit data across vast distances without losing quality or accuracy. Fiber optics is also the fastest growing technology in the world, with estimated to reach 1 billion year. In the past weeks, our institution has made good use of e-platform to reach out to maximum students and let them ride the wave of technology. On behalf of LCIT College of Commerce and Science and the Department of Physics, I would like to thank all of the participants and distinguished guests who have chosen to connect with us today.
Thank you, ma'am. Good morning, everyone. It is a great pleasure for me to introduce our respected speaker, Dr. Shikha Jaiswal, who is going to present her lecture on the topic Fiber Optics Perspective in Communication. She is an assistant professor of Department of Physics at Firoz Gandhi College, Raebareli. She studied from Chaudhry Charan Singh University, Meerut. She has completed her DPhil from JK Institute, University of Allahabad on the topic entitled Study in Fiber Optics, Applications and Measurement. She has 15 years of teaching experience of different educational institutes. She is also member and fellow of IEEE, OSI, and ISTE. She has presented research papers in 54 researches, in which 28 in international and national conferences and 26 research papers in international and national journals. She has also published a book entitled Fiber Optic Communication. Now, let us start our this session with Dr. Shikha Jaiswal ma'am. Ma'am, good morning. Shikha ma'am.
A very good morning, and
Good morning, ma'am.
thanks.
How are you?
Very fine. I'm really thankful to the management committee, the organizing committee, the principal, Dr. Archana Shukla ma'am, Mr. Abhinav Paul, who have given me this opportunity to share this knowledge with all the listeners. Knowledge means sharing, and this sharing increases and enhance your capacity as we are enhancing the capacity of our transmissions day to day, and this is giving enhancement in speed which is needed in this COVID pandemic global problem. If we won't be doing it rather before 15 to 20 years, it won't be possible for us to reach to the situation. So I thank all the listeners and I thank Dr. Abhinav Paul, Mrs. Pratiksha Pand, the convener, and the whole management committee who has given me this privilege to talk to all the students, all the listeners, all the one who has joined this webinar. My talk is on this fiber optic communication. That is, the capacity of optical communication system is rising exponentially. In order to follow the rapid increasing demand of data traffic, we need enhancement, and enhanced terms of DWDM and EDFA has been done before 20 years. Output is in front of all of you. So we should start knowing the communication, that is the global need, and need is being expected, that would be enhancing, increasing in every way. To inculcate your interest in this field and to let you know what has happened yet and what are the next future scopes. That is basically in this presentation. Thanks. I start by lead to the a very good morning to all of you. Myself, Dr. Shikha Jaiswal, Assistant Professor, Physics Department, Feroz Gandhi College, Raipur. The topic of today's talk is, today's webinar is fiber optics, the perspective in communication. We all know that communication is really important in the world. Without exchanging any information, we won't be able to exchange any ideas. And today, in the scenario of this global pandemic, this is working as a wonderful tool to get in contact with, to work according the needs of day-to-day life. For this, we need the communication to be very proper and online. This is providing boom in today's life, in today's scenario. But what has been done yet, and what is next scope in this, in the scope for this, is being discussed. The basic idea and the outline of my presentation is to start with the basic and whatever has been happened till today, and what are the future prospect of this work has been provided in this talk. So let's start with. So this is the basic block diagram of our communication system. One is the basic need is the information which is needed to be transmitted. For that we need a transmitter, and there should be a receiver section which can receive whatever the information is being sent it. So we need information. Information can be in any of the form, like it can be audio, video, computer data, or I can say that voice, video, and data. In these three forms, we need the information. One should send it, the other should receive it. Similarly, the other should also be able to send it, and the other side should also be receivable. That means that the communication should be bilateral. In our case, at this moment is unilateral. I am speaking and you all are listening. But a moment will come when the question session will be there. Then you will be speak and I could be able to handle your queries. But if it won't be a distance of many kilometers, it won't be a distance, it is just a classroom we are sitting in, and it's just a 10 meters, what will happen? In that meter distance, we have a channel, that is air as a medium. We are able to communicate properly. But when it is the need for kilometers of distance, then what will happen? You need a channel. Channel could be a free space, a wire, or a fiber optic cable. Or I can say it in two broad classification. Either it is wired or it is wireless channel. We all are using every day, like using our tab, we are using our mobile phone, we are using our modem, we are using geophiles, we are using each and every device in our daily life. But what is happening in it, that probably won't be able to know. So this channel, that is, if I can speak for a classroom, if I would be speaking in a classroom, the first bench would be able to hear me more rather than the last bench. So what is happening? The air medium is providing noise to my voice, and it won't be reached to that much amplitude till the distance of last bench. So what is happening? The channel providing some noise to the voice, to the information, and which is interfering with the transmitted information, and it is degrading it in terms of amplitude. So this is the basic communication system basic blocks. That is, we need the basic component. That is, there should be a source, or we can say transmitter. Then there should be a receiving section. मैं बोलती हूँ कोई receive करने वाला ना, that is of no point. There should be a transmitter, there should be a receiver, and there should be a medium or a channel through which the transmission is possible. And this communication channel can be any of these four we are having on the screen, that is wired, wireless, glass, water, or materials. So these are the four different classes where the communication channel could be broadly classified as. And what is the coverage, how many public is being using this communication? That can be LAN, MAN, and WAN. We all know local area network, metro area network, and wide area network. With which topology, how this network is being connected, how the people are being connected, that is the topology. It can be in the bus topology, it can be a ring topology, it can be a mesh topology, or it can be a star topology. What is needed? What is the need of this fiber optic communication? We in our talk are focusing on a channel, that is wired channel, in which the wired channel, where the wired channel is the fiber optics. Fiber communication promised extremely high data rate. If we know Shannon-Hartley theorem, where the bandwidth is directly proportional to the frequency, and the frequency on which we are working in is in terahertz. So we are having a bandwidth in terahertz. It also had a potential for transmission over long distance without the need to amplify and retransmit along the way. Possibly with the new advent of technology, but before that we used to have it regenerated, re-amplified, and retime it. Speed limit of electronic processing and the limited bandwidth of copper and coaxial cable, we were not able to process this fiber optic communication as usually as we are doing it today. It has extremely high bandwidth in terahertz, and it has extremely low loss, that is 0.25 decibel per kilometer at the wavelength of 1550 nanometer. It is very suitable for long distance communication. If you are seeing this diagram, this figure is showing that how the network is being connected, how the people are connected with this optical fiber. The red fiber shown in this figure is short haul fiber, that is for small distance, and we have a intermediate access point in this short haul fiber, and the blue one is a long haul fiber. So we are giving two types of, if there is some problem in one of the fiber, we can transmit our data to the next fiber, though the process of sending the information, dropping it to the particular points could increase, but we can have a global point, we can send it with the long haul fiber as well as short haul fiber. But this short haul fiber has intermediate access point, that in between we can drop some wavelengths, we can add some wavelengths, we can add some information, we can drop some information, so that our fiber would be free for other part also, for other services also. This is a brief introduction about optical fiber. What is optical fiber? It is a conduit. It is a conduit which is made up of silica and glass, and with the refractive index mu1, and we have a core with refractive index mu1 and a cladding which is covering it with that is having a refractive index mu2, where the core is denser than cladding, and above that we have a buffer coating over it, which is we are known as sheath also, which is transparent in color, and above that we have orange and blue color, which we already see in wherever the laying of the fiber is going on, wherever the working of laying of the fiber is going on, we can see that we have big jackets above it, that is orange in orange and blue color, or red and blue colors. This is your diagram showing the cross-sectional area, how this fiber is working. We have core, we have cladding, then we have a buffer coating, we have a buffer jacket, and then we have a black proprietary outer jacket. So this optical fiber allows the transmission of information using pulses of light. It has a very high bandwidth, low noise, and low interference, as there is no electromagnetic interference in between. It has some other problems of its own, like attenuation, dispersions, scattering, but it can't be possible. If once the fiber is cut, means the information is lost. You can't interfere that information with some other one. We have some crosstalk in between, which can be minimized by using appropriate channel distance. How this fiber is installed, we all are seeing it in our day-to-day life, that somewhere or other the fibers are being laid. This fiber is measured in fiber miles. We install 3 fiber cable within 10-mile long route. Each fiber cable has 20 fibers. So in total, we have 600 fiber miles. Currently, more than 1.5 billion kilometers of optical fiber is deployed around the world, and the circumference of the Earth is 40,000 kilometers. So you can find it how much communication is going on through this optical fiber only, that we have around 1.5 billion kilometers of optical fiber already deployed in the world. How the transmission of signal work inside the fiber? It works with the help of a very old known process, that is total internal reflection. When a ray of light moves from denser to rarer medium, and it strikes the interface at an angle greater than the critical angle, it reflects back in the same medium, then the process of total internal reflection works. So this is happening, that we have core, this is core, this is the interface in between, and this is the total internal reflection done, and the whole information has been passed through the core only. Nothing is went into the cladding, though it doesn't work likewise. It has some evanescent wave here and different types of waves which we go through and which gives the attenuation. Otherwise, attenuation aati nahi. But some attenuation work on, that is at very minute level. So this is the critical angle, that is sine inverse mu2 upon mu1. Optical signal propagates to the core using a series of total internal reflection, and it has its own parameter that is known as numerical aperture. Numerical aperture is what? That is how much what is the ability of the fiber to gather the light inside it. That is known as numerical aperture of fiber. We all know that fiber are classified into broadly classified into two types. That is, one on the depending the number of modes traveling through it, and the second is depending upon the refractive index profile. So if we say diffractive index profile, then we have two types of fiber, that is step index fiber and gradient index fiber. But if we go for more number of modes, we have single mode fiber and multi-mode fiber. This is the transmission spectrum of fiber, that is, or I can say it is known as attenuation window. Attenuation window, as I'm showing it, at 700 nanometers, what is happening? This is around 2.5 decibel per kilometer. But as we go for 850 nanometer, it is lesser than 1 decibel per kilometer. And as I go at 1.3, that is 1300 nanometers, it is around 0.25 decibel per kilometer, and for 1.5, or I should say 1550 nanometer, this has reduced to around 0.1 decibel per kilometer. So this window is known as minimum attenuation window, and this window is known as minimum dispersion window. As I said, there are two basic problems in optical fiber communication, is dispersion and attenuation. Attenuation we can manage by amplification of the signal, but dispersion is a big thing. For that dispersion, we need to restrict our distance because the pulse, the transmission signal, whatever we have sent, there is a broadening at the end of the fiber. This is block diagram of optical fiber communication system. This is source of information. This is electrical transmitter. This is optical source. Then this is optical fiber cable. Then this is photo detector, electrical stage, and destination. So whatever the information is to be sent is electrically transmitted. That means the transmitter need to change this source of information, because are avalanche photodiode or photodiode. A little technical, in technical terms, we have this electrical, then we have a drive and convert electrical into light. That means what is going on here? That is the modulation. All the electrical signal is this electrical signal, and this is light. Yeah, that means this light is high frequency radiation. This is modulated according to the electrical signal and convert the electrical signal into light signal, and then it is traveled with the help of fiber. This is optical fiber. With this optical fiber, this is coupler. coupler is again a device in optical form, and then this is again received by optical only. This is regeneration carrying on to reduce the problem of dispersion. It regenerate, it retime, it re-amplify, and then again send the signal in optical form. This optical then converted with the help of this photodetector, and this is amplified, and the signal is received at receiving end. This has been shown that the red light is the electrical signal and the blue line is the optical signal. This is optical transmitter, how the processing is going on. We need many things. It is not as simple as has been shown in the last slide. It is, you need electronic pre-processing, you have a drive circuit, then you have a light source, you have optical monitoring, then you have external modulator, then you have attenuator, then you have temperature monitoring, then your cooling process. So this is how the optical transmitter is working, and then converting the electrical signal into optical signal. This is the modulator, which is converting this electrical signal into optical. This is high frequency radiation, that is light. This is the electrical signal. It is coming in 100, like this, and this is continuous wavelength. You are seeing this is continuous wavelength. What is happening as it is modulated? What we are having? We are having 1 0 0, then 1, then again 0, and in this way. That means light on at 1 and off at 0. This is the work of the optical modulator. Then your light, when detected, it has a low noise preamplifier, then the main amplifier, then demodulator in it, and then we can receive it back in the electrical form. What are optical networks then? Now we are coming towards the basic idea of optical networks. These are the high capacity telecommunication network based on the optical technologies that provide routing, grooming, and restoration at the wavelength level as well as the wavelength based devices. Or I can say an optical network connects computers or any other device which can generate or store data in electronic form using optical fiber. And optical fibers, we all know they are the glass cylinder or filaments or conduit which carry signal in the form of light. What is the need of optical networks? We are doing fiber optic communication. We need that all the networks should be optical now. Why it is needed so what is the need, why we are needing it, so that we should convert all electrical, all coaxial cable, पहले हमने coaxial cable से fiber cable पे आए, अब हम इस fiber cable से क्या जाना चाहते हैं कि हम अपने network को totally optical बनाना चाहते हैं, because we need a high bandwidth. We have terahertz of bandwidth of our optical fiber, but the electronic instruments, the exchange we were having, they were all electronic, and the speed of electronic is limited. So we cannot reach the potential, the high bandwidth of the fiber. We all know, we all are surfing so much. We know that people open the Google window, and if we are not getting connected at high speed, what we start doing? We start tapping it 1, 2, 3, 4, because we all need high speed. And there's a tremendous growth of the connected users online, and nowadays, so it is global need. In this scenario, we need we need speed for webinars, we need speed for online class, we need speed for online forms. Everything is online at this moment, so tremendous growth is there. More and more bandwidth and intensive network application, because data browsing applications requiring large bandwidth, we need video conferencing, we need to download the movies or download the lectures. So we need the networks to be optical. These are basically the detail of the points I'm discussing in the last slide. The tremendous growth of the internet and World Wide Web, both in terms of users and the amount of time. Thus, bandwidth taken by each user is a major factor. Internet traffic has been growing rapidly for many years. Estimates of growth have varied considerably over the years, with some early growth estimates showing a doubling every 4 to 6 months. There is also a strong correlation between increase in demand and the cost of bandwidth. We have technologically advanced, and these advances have succeeded continuously reducing the cost of bandwidth. When the calls acquire the line data, the broadband connection used to be very costly, but now the cost bandwidth is very reduced. This reduced cost in turn spurs the development of new set of applications that make use of more bandwidth, and it affects the behavioral pattern also. That is what I said. We start tapping it again and again. A simple example is that as phone call gets cheaper and cheaper, people are spending more and more time. WhatsApp call, no money used, only internet. So what we are doing, we are increasing the application. So this development is giving you positive feedback that एक चीज होती है ना कि यहाँ तक यूज करेंगे इसके बाद इसकी यूजेज कम हो जाएगी. No, this is demanding the next use. So this development in turn derives the need for more and more bandwidth in the network. And this positive feedback cycle shows no sign of abating in the near future. How it is changing the landscape? Network characteristic, full redundancy, it should be highly available, it should be low latent, it has high bandwidth, fast restoration, कहीं कुछ गड़बड़ हो फटाफट रिस्टोर होना चाहिए, नहीं तो जो है क्लाइंट या यूजर जो है आफत कर देंगे. Dynamic allocation and high bandwidth efficiency and support various services. Sources are expected to provide more services at higher capacity and lower prices, and this is a positive feedback business model. That's why Reliance has invested so much. Now he has got his own fiber cable undersea. So this is that is why he's investing more. Need for high capacity network and more users. This is the optical networking. What we are having, we have a if we see the green area, it is optical network. In between, we have got blue one, that is optical cross connects. Then we have got the edge node, and these edge nodes are connected to network users. This is used to be. It was not as completely optical. The green area is completely optical, and the other storage resources, computational resources, network users, they were connected electrically before. So this was the early optical networking. So the first generation, how this optical networks evolved, it started in 1980s. Limited to fiber optic transmission system, the rest system was electrical, as I told, because thus the electronic was the major bottleneck. The received optical data had to be dropped and then transmitted again. This is known as point-to-point system. We have synchronous optical network, SONET, synchronous digital hierarchy, SDH, and fiber distributed data interface, that is FDDI. These systems were based on optical TDM, time division multiplexing, that is having a data rate of 10 Gbps or 40 Gbps. High capacity systems were built using WDM technology, and that are giving the speed of 1 terabit per second. Remember, a single phone line is only of 64 kbps, and WDM technology is giving the potential of 1 terabit per second. So that means we are unable to use the full potential of our technology in the first generation. And this was the first generation when it was only point to point. Then we have an evolution of second generation optical networks, when incoming optical signal could be switched in optical domain only. That is, no longer point-to-point networks were there. After this evolution, I will let you explain what is the difference between point-to-point networks and the optical switch networks. But for this optical switch networks, we need some underlying technologies like optical drop multiplexer, optical cross connects, optical line terminals, wavelength add drop multiplexer, dense wavelength division multiplexing. And this I have given to the new types of networks, that is FTTH, fiber to the home, fiber to the cabinet, reconfigurable optical add drop multiplexer. That is what in the last slide which I showed, that green color network, that was the first generation network when only green area was optically connected, but the rest areas were not optically connected. But from second generation, rest area started getting connected to the optical networks, and now we till the fiber to the home is reached, where then only we were able to know, we were able to see how the fiber were laid in our cities. Then it can come to the third generation optical network in which we are working at this moment, that is all optical packet switching. Then all packets are processed in optical domain. It is very much transparent to each services. It can handle any arbitrary data rate. It's not so my fiber, my system is restricted to this data rate, so it cannot go beyond this data rate. It should be able to handle it arbitrarily. And for that, the underlying technologies are optical buffering and fast switching. So we people are working in the third generation of optical networks now. This is the optical network in the third generation. Now everything is connected optically. If you are seeing that this is a big, before this only this was there, na? In the last slide which I showed, this green color जिसमें cross connect है और आपस में link थी. इसके बाद बाहर का सब जितना था that was connected electrically. Now everything is connected optically. We have internet, we have access layer, we have telephone, we have IP layer, we have mobile nodes. What is happening? Broadband connection is coming to the house, and in the house, within the room, you can't lay the fiber. Na? What is happening? You get a modem there, and that modem is connected directly to the Wi-Fi. And that now the mobile nodes are being created over there. So we have so much versatility, with so much transparency in each of the services to be provided. But for this optical networking, how the things have come up to this situation, that is the basic fundamental. And from the basic fundamental, we can come up to the new things. Like we have this optical line terminal, we have optical line terminal which is connected to optical fiber. Then we have a remote node. We have optical network units in U1, U2, U3. These are the number of nodes. And lambda U is the upstream wavelength and lambda D is the downstream wavelength. This is different optical nodes. We have optical packet switching. In the first generation network, we have point-to-point WDM transmission. Then we have wavelength add-drop multiplexing. Then we have optical cross-connect. Then we have optical cross-connect and wavelength converters with optical buffers. This is what we are doing at this moment. Optical cross-connects are there. Wavelength add-drop multiplexer are there. Point-to-point WDM transmission. We are working in a scenario that everything should be connected and it should be done compactly on the same. We should have a cross connect, we have wavelength converter, we have the optical buffers all in one way. Then we can give the optical packet switching. These switching technologies give basically two types of services. One is connection oriented and the other is connection less. The connection oriented is based on circuit switching, that is set up, connect, tear down, like public switching telephone networks. Originally only support voice, but it's not very good for bursty traffic. What is connectionless? Based on sending datagrams. Examples: packets में information को send करें, that is packet, message. Bird switching improves bandwidth and network utilization. To enhance that, we can have it in two ways. One is by using modulation. The other is by using multiplexing. That means you want to enhance the speed, and to enhance the speed, there are two ways. And for modulation, we are limited. We are limited because we can modulate in terms of intensity or in terms of phase. For intensity, we have in RZOK, CSRZ, and DO binary optical modulation. Then for phase modulation format, we have DQPSK NRZ, DQPSK RZ, then DPSK RZ, and then DPSK NRZ. So it can enhance the bit rate into length product of the communication system. But basically, this modulation formats work on with the multiplexing techniques. The need for multiplexing is driven by the fact that in most of the application, it is much more economical to transmit data at high rates over a single fiber than it to transmit at lower rates over a multiple fiber. There are fundamental two ways of increasing the transmission capacity on a fiber. The first is to increase the bit rate that requires really higher speed electronics. Many lower speed data streams are multiplexed into higher speed data stream, and the transmission rate by means of electronic time division multiplexing. The multiplexer typically interleaves the lower speed stream and to obtain the highest speed stream. So what we are doing, either we can multiplex it in the time domain or we can multiplex it in a wavelength domain. Though we have four types of multiplexing, that is TDMA, WDMA, SDMA, space division multiplexing access, and then post wavelength division multiplexing access. But I will restrict my talk to TDM and WDM. So till the electronic exchange were there, we were using TDM. And what happened with the help of TDM? This is TDM mux. This is beta per second. These are different channels, and we get the data rate of n bit per second. Now we have this lambda 1, lambda 2, lambda 3, different wavelengths are being given, and these are having b bits per second speed. After multiplexing with the help of WDM max, we get b bit per second of all the wavelengths are being sent simultaneously inside the fiber, though it's not happening over here. If we allocate a particular wavelength to each information and all the information can be sent inside the fiber simultaneously, that means it is increasing and enhancing the capacity of our system. So this is the transmission modes, bidirectional transmission. What is happening? This is the station A, this is station B, this is mux, this is dmux. This mux again can work as dmux, and this dmux can again work as mux. That's why it is known as bidirectional, single fiber bidirectional transmission. So these are the different wavelengths allocated, 4 wavelengths upstream, 4 wavelengths downstream. And in this way, 8 wavelengths are simultaneously using a single fiber. So this is the beauty of the WDM. So each signal is transmitted in a fiber using a different wavelength. As for example, the light of LED is to separate channels where each channel has a different wavelength. Can be used in single or multi-mode fiber. Can increase the bandwidth of the fiber up to 40 times. To increase the capacity is by the technique called wavelength division multiplexing. The idea is to transmit data simultaneously at multiple carrier wavelengths over a fiber. To first order, these wavelengths do not interfere with each other provided they are sufficiently far apart. This is a basic law of physics, that the wavelength doesn't get interfered when they are traveling inside the fiber if the channel spacing is kept at properly. There are some undesirable second order effects where wavelengths do interfere with each other. That is second order nonlinear effects. The WDM provides virtual fiber in that anything. WDM and TDM both provide ways to increase the transmission capacity and are complementary to each other. Therefore, networks today use a combination of TDM and WDM. The question of what combination of TDM and WDM to use in system is an important one facing carriers every day. For example, suppose a carrier wants to install a link of 60 GB per second. Should we deploy 64 WDM channels at 2.5 GB per second, or should we deploy 16 WDM channels at 10 GB per second? This is a major question. So you have 64 channels, 64 wavelengths. Each are at 2.5 GB per second. That means a link created of 160 GB per second. Or you have 16 WDM channels with 10 GB per second. The answer depends on a number of factors, including the type, the parameter of fiber used in the link, and the services that the carrier wishes to provide using that link. So one has to be very justified and optimize the link for which use the link has been provided. Using a combination of WDM and TDM system with transmission capacity of around terabit per second over a single fiber are available. And no doubt system with higher capacity of operating over long distance will emerge in the near future. This is our point-to-point communication in an optical network. These are different transmitters working at different wavelengths. This is your marks. All these wavelengths are multiplexed into a single fiber, and this is looking like it is having a multiple fiber. We have different optical amplifiers in between. The optical amplifiers are two that channels, non-overlapping bandwidths. Each of these channels can be operated at a moderate bit rate of around 2.5 to 40 dB per second that electronic circuits can handle. Because till now we are not all optical. We are having some electronic circuitry in our networks. Each of these channels corresponds to a different carrier wave. This is the spectral window in single mode fiber offering phenomenal bandwidth. We have this attenuation, this wavelength, this is 14 terahertz bandwidth in 1300 nanometer. Then we have 15 terahertz bandwidth in third window. And we have 100 gigahertz, that is 0.8 nanometer channel spacing for ITU-T standard. We have 0.8 m. Before this, it was 10 nanometer. Now it is reduced to 0.8 nanometer. That means in this area, we can have 1535 to 1562 nanometer. We can have so many channels in this bandwidth. This is very important factor for preparing our link. The channel spacing or guard band in WDM. In WDM networks, each signal on a fiber has been assigned a particular fixed bandwidth. In order to avoid interference between the signal, a fixed spacing is maintained between signal using adjacent bandwidth. Signal bandwidth is 10 gigahertz, so the channel spacing should be 100 gigahertz. So this is channels on the fiber. This is signal. इसके बाद इतनी देर तक हमें कोई सिग्नल नहीं देना, फिर ये सिग्नल कर दिया, फिर ये दिया. So that is 193.3, 193.4, 193.5. In this way, the channel spacing has been provided. It reduces the crosstalk. So we have transmitter, receiver, multiplexer, demultiplexer, routers, and add drop multiplexer. That is add drop. It is not possible कि हम यहाँ से दिल्ली तक जा रहे हैं, बाद से अगर हमको कोई वो लेना है तो हम वापस दिल्ली से आएंगे और फिर हम मुरादाबाद जाएंगे. So what we need a add drop multiplexer कि कहीं पे भी हम उसमें वेवलेंथ को ऐड कर सकें और कहीं पे भी हम ड्रॉप कर सकते हैं। तो दिस इज अ वेरी इंपॉर्टेंट फीचर ऑफ दिस WD communication. This is our mux. It has number of inputs and a single output. It generates an output signal that combines all the signals with different wavelengths. DMUX, what it uses, it serves the opposite purpose. Its input is a fiber carrying an optical signal with ith signal using channel, has at least 10 outputs with ith output carrying the optical signal using channel C for all I, that is I from 1 to N. We have very important components like EDFAs and filters. Optical amplifier used to provide gain in the wavelength of 1.55 micrometer or 1550 nanometer window, and we should have a tunable optical filter which is used to filter out a single wavelength for a photodetector to produce a tunable receiver also. This is the input. This is pass band tuned to third wavelength. So that is what we are getting. We are getting output of third wavelength. Then we have optical add-drop multiplexer. It is a pair consisting of mux and demux, where some of the outputs from demux are not connected to any of the input of mux. That means this is a demux, this is a mux. डीमक्स से जितनी वेवलेंथ जानी चाहिए थी वो दो तो यहाँ जा रही है मक्स तक, पर दो क्या हो रही है, ड्रॉप हो गई है। ऐसे ही मक्स में दो ऐड अलग से हो गई, तो यहाँ पे हमें चार ये वाली मिल गई, चार ये वाली जा रही थी। तो दिस इज व्हाट C2, C3, C4 we have dropped C2 and C3, we have C1 and C4. Again we have added other signals on this wavelength C2 and C3, and we again get the add drop multiplexer using multiplexer using optical devices are known as optical add drop multiplexers. Then we have DMUX, which is wavelength selective. That is, we have different wavelengths here at input port. We have optical circulator here. Then we have a grating here. What this grating is doing? Grating is giving support सारी wavelengths को transmission दिया और सिर्फ एक wavelength को reflection दिया. So all other are transmitted through the grating, but only 1552 nanometer is reflected back, and this reflected back is known as dropped wavelength. This is our drop multiplexer. So we have town A, then we have town B. We have this two circulators, one circulator 2, and we have this in between grating. So this circulator is doing as mux, this is demux. What these are the four at input port. These four wavelengths transmitted through the grating, only 1556 nanometer is dropped out, dropped to the B. Then this transmitted three wavelengths move towards pass through this optical circulator, and in between we have 1556 nanometer is being added from here, and this added one again added to this particular output, that is now 1550, 1552, 1554, 1556. These are not the information, these are the allocated wavelengths given. Information allocated on this particular wavelength is being dropped, and now new information is uploaded on this particular wavelength is being sent again. This is what the work is being done. The fiber brag rating is in both direction, it is bidirectional. Fiber brag rating used in optical add drop multiplexer. This is the circulator. We have four wavelengths here and drop the second one, and three are transmitted here. Okay. Now this is again this is fiber brag rating, and then again this is what we have done. From these are transmitted three wavelengths. Again, you have added this wavelength after such a long distance. You have again added this lambda 2 wavelengths, and this is again coupled, and output has been given. So that is transmitted to these wavelengths. You can add anytime, you can drop anytime, any information, and then you can send a new information on that wavelength. This is extended add-drop multiplexer. Here we have tunable fiber grating. So what is happening? This is a circulator. We have lambda 1 to lambda n, and this is the multiplexer. We have lambda 1, lambda 2, lambda 3 are being dropped and other are being sent. Now we have multiplexer, we have added these wavelengths, and again we have added this. This is extended add-drop multiplexer. So this is tunable fiber grating. That is, all the other wavelengths are being passed. So this is how the scenario has been done, how the work has been done with the help of fiber grating. We have two types of WDM networks. One is the broadcast and select network, the other is the wavelength routed network. What is broadcast and select network? Typically a local network with a small number of end nodes. And each end node is equipped with one or more transmitter or receiver. All the end nodes are connected to a passive star coupler. It is capable of supporting both unicast and multicast communication. Maybe it is either a single hop or a multi-hop network. We have every node we need a transmitter and a receiver. Each node will be able to get all the wavelengths, and this receiver is particularly tuned to a particular wavelength that it is going to receive lambda 3, this is going to receive the particular lambda. This is known as broadcast and select network, which have, it is for a local network which has small number of end nodes. This is broadcast and select photonic packet switch, which we are using in this network. How it is working? It is having a band pass filter, you have an EDFA, you have all the wavelengths here, you have SOA gates, and then you have a tunable filters. Then we have wavelengths routed network. The wavelength of the optical signal and the fiber it is using determines the subsequent path used by a signal. Since each optical signal is sent along a specified path and not broadcast to all nodes. What was happening in the last slide? All the nodes were busy. All the nodes were busy. All the nodes, total traffic that is not needed. So since each optical signal is sent along a specified path and not broadcast to all nodes in the network, because the power requirement of such a network is lower than the broadcast and select network. And this is wavelength routed packet switching. We have packet encoding, packet demultiplexing, then packet buffering. That means particular switch is able to receive a particular wavelength, and particular wavelength will work on a particular node. And this is going to reduce the power consumption, because power consumption is very high. If we are using so many wavelengths, so many information on a particular node, that means we need that much power also. So we come to the, we want to conclude the topic, that is, what are the advantages of the optical network? It has high speed capability, it has low signal attenuation, low signal distortion, low power requirement, low material usage, and small space requirements, low cost, and it is immune to the electromagnetic interference. But what are the challenges? Internet traffic has been doubling every year. New services like VOD, IPTV, dense wavelength divergent multiplexing has been developed, can transport tens to hundreds of wavelengths per fiber. Then, though the internet traffic is doubling every year, though we are able to avail with the new services, then also we have slow optical, electronic, and optical conversion. So this OEO conversion is really where we use this OEO, where the dispersion happened, we need to retime it, regenerate it, and re-amplify it. There we started, this conversion is really slowing the speed of the network. Then electronic equipment is non-transparent, that is, they depend on the data rate and protocols. So what should be the goal? The goal is the all optical. all optical. That means all the electronic component we are using within the network, that should work all optical as our EDFA work, that it works only on optical. You need not to be amplified. We need these type of devices inside our network so that everything is all optical. That is what the third generation is proceeding to. What is the today's scenario and the future prospects of this work? The evolution of optical networking from early concept to a strong progression to provide the main high capacity and flexible platform necessary to support the near and future requirement of the global network, supporting the communication requirements of a growing diversity of residential, enterprise, and scientific users. Of the switching and subsystem technology solution necessary to achieve these aims have already been glimpsed, but need considerable progress in integration techniques to overcome the deployment cost problems. There is also much research to be done at the software level to ensure interoperability between networks at a global level. Eventually, hardware and software evolution may lead to the increased levels of transparencies in these future optical networks. So the future prospect is really high. It needs a real combination of hardware and software with a very good optical switches, which not let the optical conversion slow, and no time should be there should be no time wasted in that. So the speed of the network should be very high. These are the publications. You can go through the publication. Deeply acknowledge my fiber optic communication lab, Department of Electronics and Communication, University of Allahabad, Prayagraj, from where I got my PhD degree. As well as we have the system named as Optics Simulation Software, with all the hand-on experiments on it. And we can have a field to work on long-haul applications of fiber optic communication. DJ Mr. Porwar, Digital Hangar, ITI Naini, Prayagraj, where I got experiment, the setup on which I did the experiment, ZTE 32 channel DWDM. That was the first system laid between Parmanalu and Shimla. It came to ITI for the testing purpose, and we did the testing as well as installation. And that is very beautiful system. And my collaborators, Dr. Lekha Mehra, Associate Professor, ECE GC Ajmer, Shraddha Gupta, Physics Department, Greater Noida, Dr. Pallavi Singh, Assistant Professor, ECE, Hussain College of Engineering and Technology, Chennai, Mr. Saurabh Katiyar, Associate Professor, Galgotia, College of Engineering and Technology, Greater Noida. This is some of the work I want to share. This is the paper which we wrote on efficient modulation formats for hybrid fiber transmission. Paper, the study of advanced modulation formats for high-speed internet services was done. Potentially the bandwidth of the single mode embedded fiber. We have very much different fibers, but as in the last slide, previously in the talk, I have explained that we have the 40,000 kilometer radii of Earth, we have 1.5 billion kilometers of fiber already laid. So we can't, laying the fiber is not as easy. So what we have to do, we have to enhance the speed of the laid fiber. For that laid fiber, we need some of the things to be done in the communication system itself. And for that, with this modulation format has been done. And it is basically the use of RZ format is considered in order to reduce the intersymbol interference, caused mainly by the effect of chromatic dispersion, polarization mode dispersion, and non-linear effects. This is the dispersion compensation in DWDM using dispersion shifted fiber and NRC modulation. In this, we have used a dispersion shifted fiber. We have pre-post symmetric 1 and 2 compensation techniques with RZ modulation. That is what I told, that the fiber is already embedded. We can't enhance the system, we can't update the system by laying the new fiber immediately. So what we have to do, the late system is to be upgraded, and for that upgradation, we need these techniques to remove the or to reduce the dispersion. This is the fiber link was analyzed at 10 GB per second, and the link length is 250 kilometers. This investigation is done on ITU standard G652, 653, and 655 single mode fibers with the NRZ and RZ modulations. The variation of Q value and bit error rate versus distance is analyzed to compare the performance of different fibers on single channel. This is pre-post symmetric compensation using NRZ and RZ format for a single channel at 10 GB per second. The system capacity needs to be maximized and the signal degradation caused by the transmission needs to be optimized. We have a particular or proper optimization between how much the dispersion is, how much the attenuation is, and which type of modulation can enhance the speed at this moment. A single channel 10 GB per second is investigated using two different modulation formats with different compensation techniques. This is optimization of 20 GB per second link length with duty cycle selection of RZ pulse for different ITU to 50 fibers. In this, this has been seen that at different duty cycle for a particular pulse, we have different speed, different BERs, and different OSNRs. So that is also a very important factor. The variation with duty cycle can be helpful in optimizing the length span. As we know, we are proceeding towards the third generation of optical network, and the major problem in the last network is just at the node we have the electronic speed bottleneck, and that bottleneck need to be opened up with all optical devices. And for that all optical domain, we need to get into the all optical switches, all optical add-dot multiplexers, all optical wavelength converters, and for that the team has been shifted towards the new era, that is all optical logic gates. This review paper reviews the design, classification, and comparison on the basis of non-semiconductor optical amplifier based gate and semiconductor optical amplifier based gate. Optical amplifiers, as previously I told, they are of two types, EDFA and SOA. Previously SOA was devised for the amplification purpose, but it has been seen that in this area it is working very well. Rather, amplification is being taken by EDFA. This is all optical buffer and OR gate using SOA MZI. MZI say means magenta interferometer techniques में हमने SOA को imbibe किया, and then we have a design which is working as all optical buffer and OR gate. The design and analysis of all optical and XOR OR gate using this configuration. This novel design of all optical gates using cross-gate modulation and cross-phase modulation in SOA have been suggested and demonstrated successfully at 10 GB per second. This design is giving the wavelength spectrum of all the three gates, which lies within 1554.8 to 1555.2 nanometer, which is near the central wavelength of the probe pulse at 1550 nanometer. It is found that negative frequency chirp are found for all the three gates with bit error rate 7.1, 1, and 2.1 into 10 raised to power minus 30, 31 for and XOR and OR respectively. This is all optical XOR gate using SOA based magenta interferometer. This gate is proposed with using an integrated semiconductor optical amplifier based magenta interferometer, and this design works on the differential phase modulation scheme, and the operation of the proposed gate is verified up to 120 GB per second. So the speed is continuously increasing, and the result of the gate has been analyzed in time domain for different input bit sequence, and this analysis is performed to optimize the quality factor and bit error rate. This is all optical half adder design based on semiconductor optical amplifier. It is based on the nonlinear characteristics, and this is implemented to make output of both the gates compatible for logic levels. An EDFA with suitable parameters included at the output of AND gate, that is for carry. Parity checking and generating circuit with SOA in all optical domains. You must be getting it that all our microprocessors are working in this field, and we have these parity checking circuits, generating circuits in our. So we are proceeding towards optical computing also. Though we have started with telecommunication, but we are proceeding towards all optical computing. This is all optical NOR gate using cross-gain modulation in SOA. SOA based all optical NAND gates and their comparison. So in this paper, we have used photonic crystals, which can be proved to be a better device for optical buffer. This is optical computing with semiconductor optical amplifiers. And this is ultra fast all optical 4-bit digital encoder using DPSK, or I should say differential phase modulation in semiconductor optical amplifier computation, optical amplifier Alexander interferometer configuration. There is a performance analysis of all optical NOR gates and 80 GB per second. This is all for today. Thanks for a patience listening. The session is open for queries.
Thank you very much, ma'am. Thank you for the excellent and informative presentation you have given us. Your talk was particularly appropriate at this time when we are considering new initiatives for studies through internet technology, madam. And one thing for sure, madam, without these optic fibers, it wouldn't have been possible to conduct these webinars and connect each other and also get this tremendous knowledge of your topic, ma'am. Thank you, Shikha, ma'am. How are you, ma'am?
Thank you. Very fine. Thank you so much. The session is open for queries.
Yes, ma'am. Ma'am, the questions which have been put up by the participants, one of the question is given by Mr. Rex. Mr. Rex.
Hello.
Am I audible, ma'am?
Yeah. Now it's fine.
Yes, ma'am. First question was put up by Mr. Rex. His question was, can satellite internet like SpaceX Starlink project replace fiber optics?
The satellite communication is the mobile communication, and our fiber optic communication is wired communication. So the technologies are totally different, though they are complementary in terms of the usage. We are working in mobile as well as in the fiber optic communication for getting the speed of internet, for getting various services like voice, video, and data transmission. So it's not so, they both work complementary today also, yesterday also, and will work today, tomorrow also. The speed it will provide in the, when it will work, it will provide the end user with gigabit per second, which are expecting our fiber optics to do it now only. But in the areas like mountainous region, in the areas where the fiber optics cannot lay it, there it works efficiently. And now we are having a very nice technique that till window we have a broadband connection, and after the window we have Wi-Fi connection. So this is also working with the mobile setups and your satellite plus your fiber optic communication. So replace होने का तो सवाल ही पैदा नहीं होता. It won't replace. It will work complementary.
It will work complementary. Okay, ma'am. Thank you, ma'am. I suppose Mr. Rex must be satisfied with your answer. Another question coming up by Mr. Dheeraj. What is faster than optic fiber, ma'am?
What is faster than light yet? Let me know from him. What is faster than light? So, till now, we have not yet reached all Galilean transformation, all has been worked off.
Before him, I can answer you. God's grace is faster than light.
Yeah. Every time God's grace is fast.
Every time. Ma'am, one question coming up from Kiran ma'am. What about, I think her question is not much proper. What about fifth generation networking? Madam, till now you were explaining whatever you have explained, I suppose it was on third generation. I heard the lecture just it was third generation.
Yeah,
And now
we have not
about fifth. So I suppose she should have asked of fourth generation. Or fourth is already there.
I think she's again confusing with the mobile. There we are getting it. Here it is not so.
Okay.
The both technologies are different. That's
different.
Here we are reaching third generation. We have not yet completed with the devices. The day will come when third generation will work. That means we will come with optical computing. There will be no electronic processors in our computers. It will be all optical, even at our desk. So that will be the speed would be like a light speed, and that would be creating amazing concept. And fifth generation will do what I have no idea yet. When the fifth generation of optical network will come, much more than that.
But what you told in your lecture also, that was also astonishing for us to hear, madam. Like you explained the example of that in undersea wiring you are doing, and that is
we have this undersea communication is going for around 10 to 15 years. Now, the Reliance has taken its own fiber cable, which he is using undersea for this communication. That is why it is being cost efficient, and data speed is better in Reliance and Jio.
Okay, ma'am, one more question. What is the difference between DB and DBM? Okay, this question had come up from Mr. Dheeraj, but I think this you have explained in your lecture.
It was there. Also, but he must be DBM is when your input is 1 milliwatt. When the input is any of the value other than 1 milliwatt, it is DB. That is output upon input ka ratio, power output upon power input ka ratio, and this power input when specifically is 1 milliwatt, then it is DBM.
Okay, ma'am. I suppose Mr. Dheeraj is satisfied with your answer. Good explanation, madam. Madam, can you tell one more question coming up from Ms. Vishali? What are micro and macro bending losses with respect to optic fibers?
When we are having micro, these are bending are of two types. One is micro bending, the other is macro bending. When micro bending is due to some absorption losses within the fiber, which happens due to the fabrication of fiber. But macro bending is due to the bending of the fiber. When we are laying the fiber in the city, there are some of the buildings, there are some of the areas where the bend is to be done, and this bend when has a particular radius se kam ho jayega, then it gives you macro bending. And the micro bending you cannot avoid. It is fabrication mein aap usko minimize kar sakte hain, khatam nahi kar pate hain. Though it is really coming to very less amount, because total attenuation we have reached to 0.5 decibel per kilometer with the new types of doping in the fiber.
I think Ms. Vishali is satisfied with your answer. Thank you very much, ma'am. It was really very nice. And one thing I would like to mention over here about your lecture, it was so easily explained, madam. We could understand each and every line, each and every word which you told us, madam. Very nice presentation, very nice slides.
Thank you so much. Thank you so much. There is one more question. Excuse me.
Yes, ma'am.
There is one more question I am seeing in the comment area. Which interference is happening in optical fiber? I would like to answer that also. It is inter-symbol interference, which happens due to the dispersion of the fiber. There is no electromagnetic interference. When we worked on coaxial cables, and there it was electromagnetic interference. So you people can easily understand that now mobile has started hanged up. We start having the voice. So there the interference expecting larger than what is happening in fiber optics. And that is inter-symbol interference, which is actually the new name of the dispersion. Thank you.
Thank you very much. Thank you very much, ma'am.
Hello, ma'am. One more question from my side.
What is the difference between linear scattering loss and non-linear scattering loss in fiber optics?
When we are working in linear scattering, the scattering is actually happening due to what? It is happening due to the deposition happened within the fiber at the moment of fabrication. जैसे जब सन रेज तो द एयर पार्टिकल्स कम इन बिटवीन एंड दैट एयर पार्टिकल्स की वजह से हमें ब्लू कलर ऑफ द स्काई दिखता है. स्कैटरिंग का सीधा सीधा कॉन्सेप्ट है. तो जैसे ही हम फैब्रिकेट करते हैं तो उसमें कुछ ऐसा एयर पार्टिकल आ जाए, वाटर पार्टिकल एब्जॉर्प्शन लॉस आ जाए, जिसकी वजह से हमारे पास जो लाइट जा रही है वो लाइट जो है स्कैटर कर देती है. अब उस जो एब्जॉर्प्शन है, जो उस जो भी चीज उसके सामने आ रही है लाइट के, जो ऑब्स्टेकल आ रहा है, उस ऑब्स्टेकल का अगर हमारे पास डायमेंशन जो है वो लेसर देन 10 रहता है, देन इट इज linear scattering. When it is greater than 10, it is non-linear scattering. When it is linear scattering, it is Rayleigh and Mie scattering. When it is non-linear scattering, it is stimulated Brillouin scattering and SBR and stimulated Raman scattering. So these are the different concepts, and this all happens due to fabrication of the fiber and depends on the size of the obstacle coming in.
Thank you, ma'am. Thank you so much.
Okay.
Thank you, ma'am.
Thank you so much. Thank you so much. Thank you for the patience, listener, to all my listener. And this, I would like to end up with a line that go for this area, this thing, and this is very helping. And the research in this area is stuck down for around 10 years due to the software and optical devices. So आप लोग, if the BSc students are connected, they must go for optics very well. If the concept of optics are very good, then everything is very good.
Now we put the vote of thanks in this session. On behalf of the LCIT family, I would like to thank the respected speaker, Dr. Shikha Jaiswal, who took out her valuable time and accepted our invitation. She gave us tremendous knowledge of fiber optics in the field of communication. I would like to thank our principal ma'am, who gave me an opportunity to conduct this webinar, and it is a matter of honor for me. I am very much thankful to our administrative officer, Mr. Abhinav Paul, and our science coordinator, Mr. Abhishek Kesharwani, for the continuous support and valuable advice during the preparation of this webinar. I sincerely thank the members of the working committee, Dheeraj sir, Nikita ma'am, Dr. Rashmi ma'am, Sunita ma'am, Kiran ma'am, for their valuable work and suggestions. I also thank all who have directly and indirectly helped us in this webinar. My thanks also goes to all the participants who have given their precious time in this webinar and made this program successful. Thank you so much. Thank you once again.